Hello everyone, I guess it's time to start. So yeah, book day today. I skipped it last week, but we're continuing today. We're going through the parallel and concurrent programming in Haskell book. It's a topic that I like quite a lot, but I don't get to do that much because I work with JavaScript, so mostly single-threaded stuff all the time. So this is also not only about Haskell, but also about doing something different. What did we do until now? By the way, first there is a Discord. You can join. Untitled project. See what we're working on today. Here's the link to the book. There is no affiliate link or whatever. Just a good book that I recommend to read. I think you can read online and you can buy it as well. And the repo is here. I should have linked that, but the code I haven't pushed yet the last things, but whatever. So yeah, what did we do until now? So we were here. We were checking so yeah, we went through the introduction and then the basics of parallelism, which is all about how Haskell code is evaluated. And this is basically pure parallelism, not it's about only just parallelizing about any IO. And then we were in the evaluation strategies. That's where we were looking. And I think we were left here, so yeah, we're now go through this one. But I need to I decided to change a bit the approach. So I was kind of like reading the chapter and preparing the exercises and just like reviewing them on the stream, but that was going to be a lot of work, so I will basically just go through the exercises on the stream and figure it out. And if there are any questions or any interesting topics that we find, we can just discuss as we go. But anyway, chat, how are you doing? How are you doing? Find that. Also can have to those here. Yeah, so what is this K means? What is this K means problem? Corridor here, then the K mean problem is basically, it says the goal is to partition a set of data points into clusters, like in this image. So the circles indicates the location of the clusters that the algorithm finds, more or less. So, and then partitioning the points from the location of the clusters. Partitioning the points is achieved by simply finding the closest cluster to each point. Okay. And this is something that you cannot find basically an optimal solution because it's too expensive, but there are several heuristics techniques that even if this is not the optimal result, they give you like yeah, good enough results. And one of them is Lloyd's algorithm, which finds a solution by iteratively improving an initial guess. Okay, so I think that's what we are going to do, but the algorithm is provided. So it takes a parameter of the number of clusters to find and make initial guess at the center of each cluster, then it proceeds as follows. Assign each point to the cluster to which close, yields a new set of clusters, then find the centroid of each cluster, the average of all points, and then repeat that. So go to the code. Yeah. This and which basically what's just going through the code. Okay. There's Roku strategies. So this is what we were doing in the last one, the different evaluation strategies. Okay, I guess we can add a new file. Okay, 01. Where that was the run. Here run with the statistics. Oh, I remember now. I was trying to find a way to do the statistics for these things. The previous stream was not working, but there is time, we'll get to that. So say run okay 01 is fine. So then we have data points represented as these. So we point basically x and y with all that are strict, and then 0 point, 0 point, the point, it's 0 and 0. You guessed it. And the yeah, the solution is, it should be here, so maybe I don't need to copy. Yes. Okay. So what is here? Okay. The solution. Can copy. game for yeah, by doing what am I writing? Another hidden package. Why not? Okay. Run it again. Or it's core with C, my friend. Nice. So we have that, and then what else? Here, let's generate the samples. We might copy them instead. Make file. Then this solution, and this then runs the different solutions. Okay, we'll write some of these or copy them and present everything. Yeah, so we have 0 point and find the square of the distance. Okay, so that was the square of the distance. Okay, let's keep that one. Clean them up a bit. These comments. Yeah. So that's big. This could be a line, right? Getting lost in just formatting things, but okay, so the next thing that we have the square distance here. Then the cluster should be around here. The cluster. Google, because I haven't Haskell. Backtrack now what I said. Backtrack. Okay, so it indicates the compiler that it should unpack the contents of an constructor field into the constructor itself, removing a level of indirection. For example, T, unpack float, T float and float. With unpack we'll get the construction tree containing 2 unboxed floats. This may not always be an optimization. If the T constructor is scrutinized and the float passed to a non-strict function, for example, they will have to be reboxed. Done automatically by the compiler. Okay. box. I need to learn a bit more about that. Okay. So, and then this here just defines NFT data, which is a way to evaluate the normal form. We saw it in the previous binary. I wonder what the binary is for. I don't remember from the percent. Okay, so we define the cluster. It has ID and the center. So we can have, yeah, by ID, some by center. The center is a point in the axis. Maybe just to know the different clusters that there might be, because yeah, there could be several of them. Okay, then there is an intermediate type. Where is it? Here. Point zoom. Okay. Okay. So that's defined not by us, point, but in the solution. So let's define.
I don't know what y'all think, but I think that's pretty.
So this is just, I'm going through the solution, or basically the provided code. A point zoom, and what does point zoom do? It's an intermediate type, represents the sum of a set of points, which is basically, I don't know what the int does, but this is all the x and all the y's. And the number of points in the set, so that's why the int. Like this. So we can say points x the sum and y sum. Okay. So we can add a point to the sum. It's here. Let's write it. So we can say that we're writing some code. Add get a point and a point to return point so x is y's x y count plus 1 x is plus x y. Okay. So far it compiles. And then we have the way to produce the cluster, where we compute the centroid, not the center, but the centroid. So it points some to cluster. So we get the ID. And then, where was the cluster? Client ID. The client ID is just the I, then the client cluster ID. It's I. The cluster center is a point for the X from integral count, and basically this is the average, right? From okay, nice. So this is how we calculate that. And then here it explains a bit the roles. So what do we have? We have the input, which is a set of points, as a list of points, and the initial guess is a list of clusters. And the algorithm will iterate and refine the clusters until it finds some conversions. So in the step 1, divides all the points, finding a cluster which is closer. Yeah, and instead of collecting the set of points, we just build the point sum. Okay, this is interesting. It's an optimization that avoids constructing the intermediate data structure and allows the algorithm to run in content space. And will represent the output as a vector of point sum. Then in step 2, we get the vector of point sum, which makes a cluster from each point, given the list of clusters. And then the step 2 goes back to step 1 until conversion. Okay, so this is a bit longer, so copy it and fine. Okay, so the immutable vector, and it's probably not going to be define it, but an immutable vector. So it's from the vector library. You'll have guessed it. Okay, so vector, and are we missing something else? Yes, vector cells. on. Where is the okay, let's try to compile and see. Add point to zoom, we wrote it. Add to point zoom. Ah, okay. So it's called add point. So we have one less error, but this is on. It's from wait. Compare on second. So Google again on base. Okay. Vector on. Oh, it suggested vector or. Ah, it's in base but not in preview. Data function. Okay. And one has data function for the base. Nice. Okay, it compiles, so let's take a look at what it does. So it creates a vector. What does vector create? It's a mutable vector, so it's just okay. st vector. So we replicate the number of clusters with points that are centered in zero, have ID 0, are centered on 0 and 0, and then this is our vector. We have the function add point. So it assigns points to cluster and builds a vector of points. So find the nearest. Use this function. Write point boom. Then it writes. And this, oh, okay, this is like dollar but strict. So map m add point, it's immutable, so write it, yeah, it's mutable. Minimum by compare, okay, or by this per second, and we have the list of clusters which is producing a list of tuples with the cluster on one side and the distance on the other. Yeah, the goal is not so much to understand the algorithms here, but to see how this. Okay, sorry for that. Yeah, the same connection issues. I don't know what's causing. Good thing is I figured out how to do like reconnect faster, but that's just a patch, not like a real solution. Anyway, back to the Haskell code. So this is like step 1, then step below. Okay, chat. Okay, so this is step 2. Yeah. So yeah. A vector of points on, we transform it to a list. We zip it with the indices. This is the point sum. Okay, and we're basically filtering the one. Refresh a bit the list comprehension. Rich. I mean, I get kind of what it's doing, but I will write it totally different if I had to come up with this one. Okay. Yeah, so we make a new cluster with using like point sum to cluster for each point produced by a sign. This is a slight complication in that we have to avoid creating a cluster with no points, because it cannot have a sign if there are no points, right? Okay, so here comes one last thing. Now it's called step. Combines a sign and okay, this is the whole step basically. Combines a sign and make new cluster. Okay, sounds good. So then now it comes the fun, but give me one second, or maybe I can break. Yeah, okay, like 2 minutes and I get back. I'm back. Back. The stream is still up, surprisingly. Thank you. Okay. So this was kind of like the setup. This is like the solution. Kept it in core. Then okay. And I was right there, but we can. Okay. For there. Okay, so to complete the algorithm, we need a loop to repeatedly apply the step function until conversion. This function. So okay, we have the first solution, which is sequential. Let's try to understand it. The linter will annoy us, so let's try to do this. Then printf. Printf. This okay. Not using. Okay, so let's walk through it. This is just a sequential solution. So we give it the number of clusters, list of points, list of clusters. Yeah, it's basically doing the solution that we described. And it will loop through it. So okay, n is the number of iterations. And if n is bigger than too many, we give up and return whatever we found. Otherwise, we print the iteration, we unline. Okay, so this is just to show the current list of clusters. And if we have first, so we run the step, and if we converge, if nothing had changed, we return that. Otherwise, we keep running. So this is basically was the solution, the step that we wrote in here, or we took from here. So now running. Yes, say this produces statistic. And cluster. So basically they have the code here too. Okay, we need to copy. K means stack. Now we keep the keys. Okay, we got wrong scene. Oh man, I guess I wonder how much I missed, like for sure like 5 minutes. Thank you for pointing it out. Yeah, I'm not in a break anymore. Not like this. Also hi. Yeah, how are you doing, Theoretical? Professional streamer, yes, you see. That's the life. I have now a vertical monitor where I put the things, and the OBS is on top, so I kind of forget that working in some weird Python. That's interesting. I haven't, well, I work a few streams back on Python, but that's kind of the most Python I've done. I'm doing fine. I tried the pure script like remote meetup, chat with some of the folks doing pure script, and now it's time for Haskell. And now I'm lost. So I wanted to copy the dependency. Okay, let me walk a bit back to, because I think I went through this solution all over the code. Duplicated. What? One parts will be okay. Deal with this later, but so the solution is, and this is the sequential solution. So we get the list of clusters, a list of points, and a list of clusters. This is the initial guess, and if we reach the too many then we just return, we give up. Otherwise we run the step function and we compare the new with the current one, and if they are the same then it means it converts, otherwise it doesn't, and we can return. And it starts in 0, so this is the amount of iteration. So on a par, that's interesting because I thought we had that. So let's see where does this come from. So there are no problems with the dependencies. Definitely we didn't have it. Okay, so in the meantime, for the compiles, this machine doing. So run inbound thread. The IO computation passes the first argument if the calling thread is bound. An unbound thread is created temporarily using fork IO. Run inbound thread doesn't finish the IO computation. Use this function only in the rare case that you have actually observed performance loss to the use of bound threads. Bound in unbound thread. Okay. I hope to learn more about this as the book goes on. A program that doesn't need its main thread to be bound and makes heavy use of concurrency might want to wrap its main action in round inbound thread, like a web server. Note that the exception which are thrown to the current thread are thrown are in turn. Wait, probably cannot even read it. Note that the exceptions which are thrown to the current thread are thrown in turn to the thread that is executing the given commutation. This ensures there is always a way of killing the forked thread. Okay. But we also need to run the generator. Generate the input. Because yeah, so what does the book say about that? Is the code. Okay, so maybe we can put some samples. Fine, okay, these guys. Yeah, it can find those. So yes. And samples to SRC. Yeah. So, and some. Yes. Then random package code. Wasn't. Okay, so system random was the random that I imported. Look for this random f random number generation based modeling random variables into complementary way. Let's just add it. What it does. Extra depth. Ah. More things to extra depth. I think this is the first time it's such error. With several basically rounds of extra depth that need to be added now. Okay. Some different approach to solving. Nice. No approaches of solving so. So what does Amy? This Takiyama. Haskell. Okay. Let me try game then I don't have it. Yeah. Oops.
Like a broken soul in a wonderland without angels.
The Haskell platform. It all let's give it a try with these and otherwise. Kind of failed. So basically many dependencies for now. Hope it doesn't take long. Okay. So and samples. Okay, so this fails with the same dependency. Stability. File game. Yeah. Okay, so stack, yes, stack. Okay. Okay. Oh. Doesn't show any. Yeah, so the stack. Good. Then bucket. File. How I'll open there. I'm not familiar with Caval, so I not find, but dependent. Parallel array. It was called random. Random. Game. Base parallel time technical binary. Fusion. It does. So actually there is no oh random funny. So to figure out where this is from, it's not random foo. Like the only one. Hello Danny, how are you doing? I'm getting lost in dependencies and trying to figure out how to run the book examples. Yeah, I'm working through the chapters of this book about parallel and concurrent programming in Haskell, but we are trying to run one of the examples. Cannot, so find the fusion normal. Sorry. Oh yeah, normal distribution. Let's give it a try. Extra steps. Okay, that worked. That doesn't mean that it's in the right package, but yeah, that worked. Okay, so now we can. That's cool. So Shan samples has Shan samples. So we do go up and for samples. Can run that. So tag run. Basically, this generates the input for the program. So there is point. Nice. Then there is point that pin. Okay. So what does it say? This should generate a data set of about 340,000 points with 5 clusters in 5 point bin. Okay. And now packet it for now. So what did samples? It used all the parameters that we gave it, and that this basically generates all that code. Let's not care too much. Sorry, all the input. So now we run k-means 0, 1. Okay. So tag run check, I think. Okay, yeah. This is looking for a solution, and it found it in 20 iterations. Nice. Okay, it should converge after 65. Okay, so this is the time solving it, but it said it should converge at 65, and it took just 20. Right? guess yeah, it will take 20 again, but I'm a bit surprised why. Okay, so now comes the fun part. This was sequentially. It took 420. So what can we do to parallelize this? So there was this close. Yeah. So the core got the sign, right? And I see why it was defined, right? So how can this algorithm be parallelized? The assign function, it's a map over the points, right? So map M. And this is where we'll concentrate the efforts. Okay, so then it says that these are very small operations, so it doesn't make sense to do like par list or par map that we did before, where we each of the mapping function was parallelized, each of the operations in the array. So we have a split function that we split into chunks. I think we need to move these here to I don't know if for now let's we have a bit of a mess with the code, but so no, things don't compile, make clusters. Why did I not like save the two files? Yeah, that works. Okay, so I can save both files. So what do we have? We have a split. We give it a number of chunks and the list, and we do chunk which takes the length and the quotient of the number of chunks. Okay. Okay. So how does it work? Basically we split the list and why do we use the same n? So yeah, if the list is empty, we return an empty list. If we have a list we split it at n. So we keep splitting, yeah, until we run out of, yeah, okay, makes sense. So we keep splitting until we run out of members in the list. And then okay, so we're going to split. These chunks are the ones that are going to run in parallel, and then what we are going to end up is with the list of, or a vector of point sums. So we need a way to add them together, 2 point sums, because they can be added together. So yeah, the C1 goes with C added with the C, the count of the other point, and the X are added together, and the Y is added. Then we can combine basically 2 vectors. Oh, I added these things here in power. Guess it doesn't matter. Yeah. The linter is complaining, then complaining, but this I don't really want to change. Redundant, this, okay, nice. That I did want to change. We had an extra dollar sign. Okay, so this is, what do we do here? We make new clusters, and then we fold with combine, where we assign the clusters a point. We use, okay, the strategy here. So we are using this strategy, which is evaluate the list in parallel, and each element is evaluated sequentially. This is the list of points. Okay, so this is the step that we had before, and this is the step that we have now. Is the list of points. And then, as we keep making all this code, okay, so this is similar to the previous one, the previous solution, but let's compare it a bit. Sorry. So the first strat was K strat, and we get an N here. Is okay, and that's probably the number of last. Oh. Sorry, the number of chunks. Okay, I remember a bit now. Okay. And then the rest is the number of clusters. So use the number of chunks to split into chunks, and then we have the same, or the very similar loop, but it's using the other strategy. That sounds good. So let's run it. That's an important note here from the book, that we don't need to the number of chunks doesn't really doesn't need to map to the number of processors, because we can create many of these sparks, which are these like units of evaluation that runs in parallel, and then the runtime will schedule them. So stack build thread, yeah. Okay. Yeah. Bye. Okay, so we built it. Now let's find it. Back. Classic Haskell program with runtime error, of course. I think there is the do this will probably, there is one extra argument that there we go. Okay, so it ran much faster than before. Then yeah, the other was sec. Okay, this was needed. So now if we do run sec, it takes quite some more time. So it takes around like 4 seconds, and then if we do it in parallel, takes less than 1 second. And n2 is the number of cores. And we divide it into 64 chunks. So we run it with 4 cores. Will it run fast? Yeah, not so much speed up, but this is also different because the book points that it should converge at 65, but for some reason it converted iteration 20. So might be difference in the libraries, the random libraries, or something, or the C. Okay, and then if we do it with 3, we get 66, and then it was, doesn't seems like too much of a speed up. That is here, but the ratio of a speed up that you can get actually in the book it shows you can actually get 1.8 when you add 1 core, 2.4 speed up when you add basically with 3 cores, 2.6. So the difference between these two steps that we saw that already. There is a cap of how much you can parallelize, or how much you can basically speed up, not parallel. Where were we? So let's run it with 1. Let's see. Okay, this is weird because this is even faster with 1 core. Faster than doing tech. So parallelizing with 1 core already speeds up. Weird. Oh, but I guess we are comparing different programs, right? So then we can see the speed up is quite good for 2-3 cores, but start to drop off. Yeah, I think I can run it with more, like in my case. Yeah. I do it with 12. It increases probably the overhead of communicating between them. Then where is the output? Parallel. Okay, this is event log, so
the voicemail box of Kino.
thread scope. Yay. What is running program?
Just wait for the tone.
Threaded
Is not available right now. If you need further assistance,
Let's see.
enter pound now.
Compile again. And run this.
Number and a message after the
We
tone.
get we don't get the output. Did I need to run it to get the output?
Goodbye.
Stack run. Plus RTS and L. Yeah, okay. Let's go. There we go. Okay, this looks a bit more like the book. But let me run it with 4 cores. So the L was needed. And this looks really like what the book shows. So what do we have here? First of all, there is some time that we spend for the parallelized part program. Yeah, that's the sequential section at the start where the program is just reading the input data. That takes almost a second. It's quite long. And then the parallel section, the book says it looks quite good. But there are these chunks. So this here looks, what's happening here, for example. Here is a bit weird because there is no garbage. Okay, so it's probably one processor finishing chunk, I'm assuming. Then there is some garbage collection here, and here it's, sorry, this is weird. These are parts where we have a lot of, at the beginning, a lot of garbage collection in the main thread. Yeah, so this is what the book shows. There is a huge garbage collection here. Then there is a huge here, and this was the parallel step. It's quite garbage good. Yes. It. Yeah, so there is a gap in here between 7, 8. I think it's this gap, yes, this gap that we already kind of talk about. And there is a lot of heavy garbage collection activity. Okay, so the fact that we are splitting into chunks is causing the work. And that's why we are not achieving full speed up. The sequential version doesn't need to do it, but this version. And it's because we are using list and we slice the list. Okay, that's an interesting program to work on. So we slice the list, and that takes ON probably, or whereas vector is O1, so we could and then if we zoom in in here we get all these camps, right? Exactly like the book shows. This is the parallel path. Okay, so there is the loop. There is this loop where we are comparing things here and we are printing things, so there is some sequential execution happening, like probably this, but this is still, sorry, I'm pointing to the wrong, yeah, so probably this, but this is not. Oh, yeah, and then these cores run a bit longer than the others. Event. Okay. How do I find all this? Go figure where. So it's somewhere around 07745. Okay, so 07755. Here, but I don't know. Okay. We'll find each other. Find. Okay, I was able to do this. Okay, so it says that make foreign calls. Yeah, here, this section. So there are the things that are happening. I'm making foreign calls. So yeah, this indicates IO, which could remind us. Yeah. So basically this means that we are printing, right? And then there was the law, which are it's handles. So where is it? Which is the one that says computer architecture formula gives a theoretical speed up in latency when we parallelize things. This is so yeah, if we are doing things in the sequential part of the program, we'll get paid. Okay, so we can now count line of then we stack and build. And we should get a different result. Oh. Okay, yeah, it converged. I was expecting the print statements, but let's go. Well, we have some of those. It's yeah. I was a bit faster, but this coordination that we're doing between, so the two processors run a bit longer, and then we do something, the comparison still in parallel, and then we continue. Sorry, it's sequentially, and then we continue in parallel. Okay, we can also use thread scope to visualize sparks. And then let's take trace. Wait. Spark creation. Spark pool. Spark pool size. Okay, why do we see only? Can also use telescope to visualization. Spark. Different metrics, but in the example they show all in several. Okay, so this is this is what we did. So we are splitting this into 64 chunks. So in each iteration we create 64 spark, and then they will start being completed. 30 else. We should be able to see this is the creation, and then they get consume all of them here. This was kind of like a faster cycle, right? So this is quite interesting. Okay, so it says that in the book example they are created in different cores. but in this case they're all in the same one, so it should, like the runtime, it's trying to move the workflow, but there's differences probably in runtime here. Okay, then we can play around also with the amount of chunks. So if we, with 64 it running 0.53, we put like 4 chunks and it run a bit lower. We put 10, sorry, will be similar. Put 500, it will probably be the 1000. So the more we chunk it, it will not basically improve. We were creating like, yeah, you see, like 1000 chunks. It shouldn't like speed up things, but there is like a sweet spot between 150 and 100, which is the best for this program. And yeah, the more you add, there is overhead here. So. Okay, then start kind of, the book basically starts explaining some stipulations of things you can do. And yeah, I think that's it. That was the interesting part. This book, then it goes into, sorry, not this book, but this chapter. A way to parallelize. Okay. Yeah, I think that's it for this chapter. It mentions a few other things, but yeah, we got to see some of the graph and effects, so I think that's good for this chapter.